Okay, seems right. Great. So welcome to the third seminar of this series. We are very happy to have Zoltan Bajnok with us today from Wigner Center for Physics. And he will talk about the O4 sigma model and perturbative and non-perturbative physics. So I leave it to you.
So thank you very much for this opportunity to present this recent work in this nice webinar. It's my honor. Actually, I was a bit surprised because we are not really expert in this subject, and then I was asked to explain. So I will take a kind of pedestrian approach and then introduce sort of chronological way how we figured out this resurgence structure and asymptotics and transseries in this particular model. Just to put the basic question I would like to answer is that whether it's possible to get non-perturbative information out from just the perturbative coefficients. So should you have any question, please stop me and ask. Yeah. So put it a bit more mathematical way, I would like to take some physical observable, which is a function of the coupling constant, which I will denote by alpha. And then let's assume I can calculate these perturbative coefficients, C0, C1, and up to some large number. And the question is whether just knowing this coefficient, I can tell you what are the non-perturbative corrections to this physical observable. In particular, in the model I'm going to analyze, the non-perturbative correction will go like e to the minus 8 over alpha. So you see it's e to the minus 1 over alpha, so it's non-perturbative. And then it has some expansion in alpha, multiplying this non-perturbative piece, d1, d2, and so on. So the question is, if we know enough C coefficients, can we get these D coefficients or not? And the answer to this question will be yes, and this is what I'm going to explain. I'm going to explain on the example of this O4 sigma model. So this is a recent work which was done in collaboration with Michael Abbott, who was actually a postdoc here in Hungary, and he's just leaving to Yale. He got a postdoc position there. My colleague János Balog, Árpád Hegedűs, and our former postdoc Saideh Sadayan, who went back to Iran and she got a position there. So this works, what I'm going to explain is based on these two papers, and you can look at the archive. So this is the plan of my talk. It has basically two parts. So the first part, in the first part, I will explain how to get the C coefficients. And then even it is divided by two parts. In the very first, I will show you this O4 sigma model is a quantum field theory, which has a Lagrangian. So you can do just usual Lagrangian perturbation theory, and you could calculate these perturbative C coefficients. But of course, this is difficult. So, and we cannot usually go very high orders. So why this model is very nice and important for us, that this is integrable. And since it's integrable, we can go much beyond that. We can calculate much more coefficients. So this is the first part of the talk, to introduce this model and to explain how to get the coefficients. But if you are lost in this particular part, then you can rejoin again later when I already got the coefficient, and I try to investigate those coefficients and see if we could somehow obtain this non-perturbative D coefficient, the non-perturbative effects out of the perturbative. This is the second part of the talk, and I will introduce the Borel plane, and I analyze the Borel function, the analytic structure of the Borel function, and then I will use this analytic information to build up the physical observable purely from this perturbative coefficient, I use this median, resummation, and I will show you how you can get this non-perturbative piece. On the way, we will use resurgence and transseries, but I'm not really an expert on this part. I could see in the audience you have probably person more expert than me, so you can ask maybe also them. So I would like to just show my approach, which is based on this exactly soluble O4 sigma model. So what is this model? So this model, in the case of the ON model, you have n scalar fields in 2 dimensions. In the O4 model, you have 4 scalar fields. They are living on the unit sphere. And then you would like to couple this theory to a magnetic field. So this is the Lagrangian density. It has basically the free part together with the constraint. And then this is an Euclidean version. And we just take one of the conserved ON charges, say rotation in the 1, 2 fields, and we take the density and couple to this magnetic field. This coefficient here, this pair coupling constant, is just multiply the whole Lagrangian. So classically, it's a scale invariant theory. And it was designed such a way that if you could calculate the Hamiltonian is the same like the theory without the magnetic field minus h times this conserved charge. So this is exactly this Lagrangian. And the way you do calculation, perturbative calculations, you say express one of the scalar fields in terms of the other, and you assume they are very small, and then you make just the path integral in these variables with this Lagrangian. And then, of course, this is divergent. So you do the calculation in this capital D dimension, and you use dimensional regularization. The result is proportional to volume, and what multiplies is the free energy density. And we would like to calculate this free energy density as a function of the magnetic field. This is the observable we would like to calculate. But in order to compare to the integrable description, it's actually useful to make a Legendre transformation. So we can introduce the density instead of the free energy, the density of particles, and the ground state energy as a function of density, which is defined in this way. So this is the definition of the model, and you see this is a generic quantum field theory, which has a nice Lagrangian description and the path integral formulation. So how does the calculation go? So it's a usual perturbative calculation. For example, this is the result of the 2 loops. And then you really have to evaluate diagrams like written here. And we did it some time ago. But as I told you, this is some singular, this quantity is singular in the epsilon goes to 0 limit. So you have to renormalize your theory, especially you have to renormalize the coupling. So you introduce the renormalized coupling. This is G tilde, but this coupling is running. You could calculate the beta function. And you could express the free energy instead of the bare coupling in this running coupling. Leading order, they are the same, but higher order, you will get corrections. As a result, you can calculate the free energy density as a function of the logarithm of this mu, which is the renormalization scale divided by h. This is dimensionless quantity, and this running coupling. But of course, this depends on this mu. So it's a good idea to introduce a renormalization group invariant quantities like the dynamically generated scale, which is defined in terms of this mu and the running coupling in this way. So once you introduce this this lambda, then further, just one notation. I will denote delta 1 over n minus 2. This is a quantity which appears in many places. So from now on, in the O4 model, this is 1/2. Usually, this is like what I said. So once you introduce this dynamically generated scale, actually, this theory is a very nice toy model because it is similar to QCD. classically it's scale invariant, but if you do the calculation at the quantum level, then you will see this dynamically generated scale. And then you can calculate the scale in different schemes. And we did the calculation in the MS bar scheme. In the MS bar scheme, you can introduce the expansion parameter in terms of the logarithm of this magnetic field divided by this dynamically generated scale. So you can introduce a running coupling constant alpha tilde by this relation. And what is nice about this coupling constant, if you calculate the free energy density, it's basically a power expansion, no log, nothing else in this alpha tilde quantity.
Sorry, Zoltan.
Yes.
Alpha tilde is no longer running, right? Because it's determined in terms of invariant quantities, or not?
No, I think this is just why do we say it's a running coupling? It's just a notion, I guess. No? Maybe it's not.
Yeah, I think
maybe it's not a good word for it. Yeah,
if you take mu instead of h, I will call it a running, but with the fixed.
Yeah, I see what you are saying. Yeah.
Right. Okay. Never mind.
Yeah. So this is a nice coupling, definitely, and then it resums this log, and then the log squares and so on. So, and this is exactly what we use actually on the integrable description. But the integrable description is formulated for the density and the ground state energy. So you introduce another coupling after Lejeune transformation, which depends on the ratio of the density divided by this lambda ms bar, basically. So if you introduce that coupling, then the ground state energy divided by rho square is an expansion in this alpha. And this is the quantity I would like to analyze in the whole talk. We will analyze rho and epsilon separately, but mostly this ratio epsilon rho divided by rho square, which has this nice expansion. And this two loop result on the top of the page leads to this very nice expression just with the free coefficients in the bottom. If you were infinitely clever, or you had many time, you could calculate lots of coefficients. And then this is a complicated model, but in simpler model like 5 to the 4, Marco calculated your company like maybe 6 terms in the perturbative expansion, or maybe more. I don't remember exactly, but in order for the analysis we are going to make, we will need much more terms. So we will need hundreds and thousands of terms. So so you see, it's impossible to get them from perturbation theory. So we will switch to the integrable description. And I should say, even in the integrable description, usually it's impossible to get so many terms. And this is a very lucky situation that in the ON models and a few similar models, you can do the same. So in the integrable description is completely orthogonal, the Lagrangian description, because it doesn't use the ultraviolet degrees of freedom, but the infrared one, which are the particles. These are massive particles, which transform in the vector representation, and they have a complicated scattering matrix. So when they scatter, because this theory is integrable, then a two-particle scattering will lead to two particles, but because it's a vector representation, it's a big matrix. It's an n square by n square matrix. So it's a complicated but known matrix. But what is nice about this magnetic field we introduced, and this is one reason we introduced this magnetic field, that we can diagonalize the action of this conserved charged Q1, 2, and there are going to be particles charged +1, -1, or no charge. So if we just analyze the dispersion relation of a one-particle state, so the energy of a particle can be parameterized in terms of this rapidity, m times cos theta, such that the momentum is m times sinh theta. So this is basically what I'm drawing here. This is the dispersion relation cos theta as a function of theta. And then if you analyze a particle which are negatively charged under this magnetic field, and then you increase the magnetic field, then it will have a negative energy if h is larger than m. So for large enough h, particles with this negative energy will start to condense in the ground state. But they are fermions, so they cannot occupy the same state. So you will have a distribution of particles, which I denote the density of particles by chi of theta, which fill an interval between minus b, and this b depends on the magnetic field. So this is the structure of the ground state. And we would like to describe this ground state. The way we describe it, we first move a bit to finite volume and analyze a multi-particle state of this negatively charged particle which condense into the vacuum in a finite volume. So we are in a finite volume of L with periodic boundary condition. We put like n particles and we analyze the momentum quantization. And then this is an integrable theory. So these particles, when they scatter on each other, they scatter just diagonally, pick up a phase, no more particle production. And the scattering can be calculated from this big scattering matrix from integrability, and it's written here. So this is the scattering of the particles. There are many of them on the interval, and the periodicity requirement for the wave function, if the volume is large enough, it's basically if you move a particle around the circle, you pick up the translational phase e to the IPL, and additionally, you also pick up the scattering phase, scattering all these other guys. So this is the quantization condition, which is called the beta-Young equation. Taking the logarithm of this equation and differentiating with respect to theta, you can derive an integral equation for chi. This is how integrability works in this case. And this equation, what comes out, I will call the thermodynamic beta-ansatz equation, or TBA for short. It contains the kernel, which is the logarithmic derivative of the scattering matrix. So this is an interlinear integral equation for this rapidity density of the ground state. And then if we integrate this density, rapidity density, then we got the full density. If we integrate with the dispersion relation, we got the full energy. And then we can recalculate the magnetic field by minimizing the free energy. So this is the integrable description, how you can solve the problem exactly. But it's highly non-obvious how you could expand actually this rho or epsilon in terms of age for large age. And this expansion, especially for go for high orders, it resisted solution for years. And that was a breakthrough by Dima Volin, who suggested a very nice procedure actually to calculate the perturbative coefficient very high order and very efficiently. And his idea was to introduce, instead of working with this chi density of particles, let's try to work with the resolvent. The resolvent is an analytic function on the whole complex plane, except a cut, which goes between minus b and b, such that the jump of the resolvent on the cut is nothing but this chi. So he introduced this resolvent. And then it's also useful to introduce the Laplace transform of this resolvent, because it's easy to express the density from the resolvent itself as the residue of the pole at theta equals infinity, because this is just the integral of chi. But to get the energy, the resolvent is the Laplace transform of the resolvent is much better, because it's basically the Laplace transform at the position 1/2. So you see these two quantities are the two sides of the same function. And then you can easily switch from one to the other. So the idea was that let's analyze this function. So I have the density distribution of the particle, this chi of theta. And he suggested two expansions. One expansion of this function, or the resolvent, expansion of the resolvent near the origin. So he made an ansatz in terms of a function which has this cut, the square root of theta squared minus b squared to some power. So it's exactly having this cut structure. And then for each function, additionally, a 1 over b expansion. And this b is related to h, and then h going to infinity actually means b going to infinity. So we are expanding this quantity in 1 over b. When b goes to infinity, basically we are performing these integrals on the whole line. And that can be solved, or the half of the line, this can be solved by Wigner technique. So if instead of focusing in the middle domain, we would focus on just the edge region near b, then this integrals up to exponentially small correction goes from minus infinity to 0. And that equations can be solved by this Wigner technique, which means you can calculate the resolvent written here for large b. So this is the leading piece here. And you can also parameterize the correction for the resolvent as an expansion in this 1 over b. So basically you have two ansatz. You have one ansatz for this resolvent as a function of theta in terms of the c and m coefficients. On the other hand, you have an ansatz for the Laplace transform of the resolvent in terms of this q and m coefficient. And demanding that these two descriptions are equivalent to each other in an overlapping domain, you can get nested or recursive linear equation which can express the c and the q coefficients in the same time. So it goes that this leading piece will determine the leading c, which determines the next q, which determines c, and so on. So by this matching procedure, yes?
Can I ask, sorry, can you be a bit more, can you show us a bit more precisely what is the parametric dependence of this exponentially small correction that you neglect? So since exponentially small correction will enter in the resurgence story, I just wanted to see whether we are talking about the same somehow. So that.
So this is actually extremely important. The terms we are neglecting now for a later and more complete analysis, which could give not just the perturbative expansion, but also the exponentially small terms, but we couldn't put into analysis yet. But to show how what I'm actually neglecting, I can show. So let's take this energy, for example, which you integrate from minus b to b. Can you see? It's here. So this is, and then let's shift the variable to the z, which is twice theta minus b. So this means the z integral goes from minus 4b to 0. Okay, so the your resolvent are of z is a function which is 0 for z larger than 0 and non-zero between minus 4b and 0. Okay, so the resolvent lives here, but looking from this point of view, you can assume that it lives on the whole negative line. So what I'm neglecting, I'm replacing this integral going from minus 4b to 0 to an integral going from minus infinity to 0. This is basically how I neglect those terms. So I'm solving the integral equation such that one of the integral boundaries is no longer, say, minus b, but minus infinity.
Yeah, no, sorry. Maybe I was asking if you know a bit more precise the parametric dependence of these exponentially small terms. So these are of order e to the minus what? A bit more precisely.
Yeah, it's e to the Yeah, naively, if you just look it e to the minus 2b, I think. Yeah.
E to the minus 2b, no other parametric
But if you check it carefully, the coefficient of e to the minus 2b, then you will see it's 0 actually. Somehow it comes from a residue of a pole, and then this residue happens to be 0. So now, so maybe it's e to the minus 4b, or maybe even higher.
Okay, thanks.
Okay, sorry, yeah. So coming back to this matching procedure, what was the breakthrough Dima made is that instead of solving any equation, just take these two ansatz, match these two ansatz, and then you can determine both C and both Q coefficients. And then if you determine the C coefficients, then you can calculate rho. If you determine the Q coefficients, you can determine this epsilon. And using this coupling, how this coupling constant runs, this alpha is written in terms of B and rho hat, which is rho hat is basically rho just starting with 1 in the expansion. So using this relation, you can also calculate epsilon divided by rho squared as a function of alpha. So this is how we can get these perturbative coefficients from this nice matching procedure. So what are the numbers, what you will see? So if you calculate this rho and you normalize out some dimensionful quantities such that it starts the expansion with 1. So it's an expansion in 1 over b. And then this is the first to third and so on. So you can go high orders. I will explain in a minute how high. But I would like to just point out the structure. The structure is that you have some rational numbers, and then you have this log2 multiplied with the rational numbers at the first coefficient. And then the second, you also can have a square. And then later, if you go to higher coefficients, you will also see odd zeta functions. So the structure of these perturbative coefficients are basically polynomials in A and odd zeta functions, such that the highest degree, transcendentality degree, if you associate to 1 to log 2 and the index of the zeta function to zeta, then the transcendentality should be less than the index of this perturbative coefficient. But everything can appear which is below this. So if you calculate higher and higher orders, they are longer and longer and messy expressions. But using this method, Volin could calculate like 22 coefficients, and Marcos and Thomas could calculate like, I think, 44 coefficients, if I'm not mistaken. And then we calculated 50 coefficients. We could calculate a bit more because they both focused on generic UN models, but we focused only on the O4, and in the O4, these equations are much simpler. But there are not many insights from these 50 coefficients. Just before explaining how you could do a bit better, let me tell you that you can do the same in this free energy, which is epsilon over rho squared. And then you can express this quantity in terms of this alpha coupling, which is related to can be related order by order. And what is a bit surprising, that the expansion of this free energy density as a function of alpha, this log2 completely disappeared. So you have only odd zeta functions. But still, it's true that up to an index, you can have zeta functions such that the transcendentality is less than the index of this perturbative term. So we can calculate all these coefficients. And then just, I can't resist actually to point out this nice fact and nice result by Hasenfratz, Major, and Niedermeyer. So if I presented two calculations for you for this free energy density, the expansion in this magnetic field for large magnetic field. The first calculation was the perturbative calculation based on the Lagrangian, And the expansion was an expansion in H over lambda. However, in the perturbative description, we used infrared degrees of freedom, and then it was an expansion in H over M. Just comparing these two perturbative expansion, you can actually match lambda to M. So you can express the dynamically generated scale in terms of the massive of the particles. So it's a beautiful result. It would be very nice to have something similar in QCD. So we could calculate, I don't know, the hadron masses in terms of the quark masses. So it's really nice and kind of surprising result. And the way Ferenc Niedermayer first conjectured this formula, actually, he calculated these two expansion, especially the TBA calculation numerically to several digits. I think it was like 6 digits or so. And then from the 6 digit, he could see that this should be 8 over E, just looking at the numerical value. And then later he proved it analytically. Just this is the history. But once you know the relation between H over N and H over lambda, you can transform this expansion we got in the TBA, actually the language of the Lagrangian, and then you will know all the perturbative coefficients from the Lagrangian language too. Yeah, so as I said, these are longer and longer expression and not very enlightening. So what is a bit more enlightening, actually just to see what is the numerical value. But in order to go higher, because analytically we could calculate only 50 coefficients, but numerically much more. So what we did, we just calculated the first 2000 coefficients for 7000 digits. For rho, same for epsilon, and we could calculate like the 1400 coefficients with 40,000 digits for epsilon over rho squared as a function of alpha. So having that much perturbative coefficient, we could analyze the asymptotics, how they behave if the n index is very large. And we realized that if we make this combination, for example, I will explain for chi. So if it grows like n factorial. So if you divide by n factorial, multiply with 2 to the n plus 1, that it will have a constant asymptotics. Actually, this asymptotics has two pieces, just a constant and an alternating part. So you can switch to another series, which is the even and the odd part. And like here, what I'm showing in the bottom, in the even part, it has a constant asymptotics plus a 1 over n correction and so on. And then to see that it really grows like n factorial and what is the constant, you can speed up this convergence by going to the Richardson transform, which means you can make a transformation on this series, AN series, which is the even part, just multiplying with n plus 1, the n plus 1 piece minus n times AN. And you see this trick improves the convergence in n. So the constant part is not changed, but the correction is, instead of being 1 over n, it will be 1 over n squared. So if you repeat this transformation many, many times, because we have enough terms, we can do it, then you will see that what I'm plotting here, I subtracted from this AN series, this asymptotic A value, and I just plot the difference. And then you see even the 100 Richardson transform is pretty constant. So by this method, we can read off this A coefficient very precisely. So let's see what we get.
Zoltan, can I ask you another question? So how did you choose n equal to 4? I mean, 04 in particular, as if I'm not mistaken, is special because there is some sort of, the kernel of the TBA is similar to the one of the Gros-Neve, and the Gros-Neve model at 04 also is special because the kink, the fermion decays. there is a special, something special about O4, no? So,
absolutely, yeah.
Why did you end up with the 4?
Yeah, it's a good question. And it has a kind of simple answer, actually. Yeah. I have to learn how to move in this file. So maybe every ON is special. O3 is definitely special because the kernel is rational. This is the simplest model. And you would think, I would think, O3 is the simplest possible model. And even in O3, we know there are instantons. So we started to analyze this whole problem in O3. But the difficulty with O3, I'm showing this parametrization R of theta, the resolvent as a function of theta. It has additionally to this, I'm showing an ansatz for this function, which contains square root of theta square minus p beta square, having exactly this cut structure. But for other ON models, this is for O4. For other, even O3 or other ON models, this is not the full ansatz. This ansatz will not work. You introduce a free parameter constant C and M, and here you additionally, you have to introduce log theta minus b divided by theta plus b. So that resolvent has also a log dependence on theta. And which means you have to make this fitting procedure for a 3-index C, not a 2-index one. And then we couldn't go that high order numerically, that in the O4 case. So the O4 is simple in this sense. And also I should say that the asymptotics of the resolvent, what I'm showing here, this is very simple. So for any other ON models, you have also a piece S to the sometimes S. So the analytic structure is more complicated in all other cases. Technically, in this ansatz, I have only just 2 index quantities which I can easily fit, but in any other ON models, I have a 3-index CNML quantity, and then it takes much more computer time. So in the O3 model, now we can have like 260 coefficients after running 2 weeks. So that's the reason we choose O4.
Okay, thanks.
Yeah. So we have seen that the asymptotic of the CN coefficient, if I make this combination, I mean, this is the definition of the CN, and this is constant. So, but on the other hand, we see that the chi coefficients are growing like factorials. So first question, what's the meaning of the perturbative expansion at all? If it's growing, it's asymptotics, what can we do? And the usual saying is that we should go to the Borel function. And then why I was always, I heard many talks and they say, let's go to the Borel plane, but why to the Borel plane? But I learned from your paper, Marco, that there is a nice argument in the path integral. So if you perform this path integral for all configurations, and then you do it in 2 steps, and the first step you perform when the action has some constant value first, and then integrate for the possible values of the action. This is basically the Borel function. So you can think of this Borel function is in the path integral language, that you are just performing the path integral for a given value of this Euclidean action. So it's a very good function. So what we are doing, instead of analyzing the perturbative.
May I make a comment? Yeah, this argument is a little bit, it's a little bit misleading, because this is supposing that the singularities are due to Euclidean configurations, but this is not the case in this case. It's not, singularities are not due to Euclidean configurations of the path integral.
Well, I didn't talk about singularities yet. No, I'm trying to argue why we go to the Borel plane. Yeah. Okay. maybe we can say we go to the Borel plane. I can give another argument. So we know how this chi coefficient know, like factorial. So if we define this C and define this Borel function bt as Cn times t to the n, then this function will have convergence radius 1. So this means it will have a nice analytic structure on this T plane, which I call the Borel plane. And to understand a bit better this analytical structure, what we can do, having already calculated many C coefficients, we can just approximate this function a bit away from the unit circle when it's convergent by, say, a Paddy approximant. Paddy approximant takes care of the poles. So if you use some 100 order Paddy approximant, then you can plot the poles of the denominator. It's exactly given here in blue. And then you will see in this O4 case that you will have a pole singularity at location 1 on the real line. And then you will see many, many poles condensing starting at 2, and also many poles condensing starting at -1. So maybe that's why it's a good idea to go to the Borel plane, because you have a well-defined analytic structure with poles and cuts. What you can read of from this quick approximation, that all the singularities are on the real line. Some of them on the real negative and some on the real positive line. And in order to get back a physical value and then move from the Borel transform back to the original physical quantity f, you have to integrate actually on the positive real line. So if you are in a lucky situation, when there are no poles and singularities there, then your physical quantity is unique, and then this definition via the Borel function will give a unique answer. But in our case, you see we have poles and cuts there. So we have to shift away the contour. We could integrate, say, a bit above or a bit below, but the result will be different. We will have an ambiguity. For example, from the pole, we will have an ambiguity which is proportional to e to the -2 over alpha. So you see, this is exactly a non-perturbative term. The non-perturbative terms are related exactly to the singularities on the real line. In order to get a better calculation of the physical values to integrate above and below, the Paddy approximant is not good enough. So what is better if you use some conformal mapping? So what is this conformal mapping? So we have this Borel function, which has a singularity on the negative and the positive real line starting at 1. So since there are no other singularities on the complex plane, we can use this conformal mapping, define this u variable, which maps this whole complex plane except the cuts on the unit circle, and our new function, which is defined as an expansion of this u variable, will be convergent on that circle. All the singularities are at the borders. So this is it's plot how these constant u lines behave on the original t plane, and then you see if you put u higher, then you can approximate your function below the cut better and better. So truncating this series in the u variable and performing the integral, then you got a good approximation of your function. You could get this f plus and f minus, and we used, I don't remember, maybe 1,000 terms in this conformal mapping to calculate this f. And then what we did, we asked the question, so we got this f plus and f minus, but how does it compare to physics? But what is physics? Physics, the solution of the integral equation. So we solve numerically the integral equation. Technically, we parameterize this density, rapidity density chi by expanding in terms of Chebyshev polynomials. And then this made the problem discrete, and then this linear integral equation was basically a matrix problem, what we could solve. So we got a a numerical value of rho and epsilon with at least 30 digits precision. On the other hand, we used this perturbative coefficient with the conformal mapping, and we calculated f plus minus, and we just compared the two. The first observation is that this conformal mapping integrals had real and imaginary parts. However, this solution of the TBA was obviously real. So every imaginary part that came was of course due to the ambiguity, and then they shouldn't be there. But we could fit this coefficient. So we fitted the imaginary part. We observed a piece e to the minus 2 over alpha, and also we observed this e to the minus 4 over alpha times a perturbative expansion, and then we fitted from the evaluation of these conformal integrals, we fitted these coefficients. I just present here the first three. Of course, if you could say I shouldn't worry about the imaginary part because I could just average f plus f minus and it would disappear. But what was a bit more surprising, that if you do so, and so you analyze the real part, that the real part still deviated from the TBA result, which we believe this is the exact physical value. And the deviation was exponentially small, much more small, so even smaller, sorry, yeah. E to the minus 8 over alpha times an expansion. And then just comparing to the numerics, we could also fit these coefficients, this D1, D2, D3, and maybe even D4. So what I'm going to do now is to explain and calculate this D1 and D2, I should say analytically, but not really analytically, just to conjecture what they should be, what the analytical value for them should be. And the way I do it, I use asymptotic analysis. And this is a nice machinery which goes on under many names. It has also resurgence, trans series. This is a nice theory, and I'm just learning this theory. I have to confess, I'm not expert on this, and I learned many things from this review of Daniele Dorigoni, which is on the archive. This is a very nice introduction. I think it's good to start. Also, there is a recent review by Aniceto, Bassar, and Schiappa that you can read. And then let me just tell you that in the Newton Institute in Cambridge, they are just organizing a program about resurgence and this topic. And that is going to be a school. So if you are interested in, then I suggest to visit this school, which is going to be in the last full week of March. So it has a theory, and then this theory introduces this alien derivative. And then let me just explain in terms of what I would like to use. So let's assume you have this function psi as a variable z. In our previous analysis, this is basically 2b. So I have this psi starting at 1 and with some expansion coefficient Sn divided by Zn. And then, as in our case, this Sn grows factorially. So if I divide Sn plus 1 by n factorial, then this Cn coefficient will have some constant asymptotics. And I will switch to this Borel function, which is defined by Cn to the t to the n. Okay. And then I'm just telling that the asymptotic large n behavior of the Cn coefficients are in one-to-one correspondence with the analytic structure on the Borel plane. This is obvious, but I would like to make it a bit more specific. Namely, if you take this Cn coefficient, then you can decompose this. Say in the alternating part, you have some constant p minus, and you have 1 over n correction, which I denote by p0 minus. And then the next correction I will parameterize like p1 minus divided n times n minus 1 and so on. And similarly, you have a term, a non-alternating piece, leading piece, P plus, and P0 plus divided by n, and analogously P1 plus divided n minus 1, and so on. And then I could have also subleading pieces, which goes like 1 over 2 to the n and a similar expansion. So what I'm claiming now, that if you assume that this C has exactly this form for any n, because it's valid for large n, for all n, then you could calculate, you could sum up piece by piece this guy. For example, if you sum up this P minus piece, then you will see it will lead to a pole like P minus divided by 1 plus T. So it's a pole at T equals minus 1. If you sum up the next guy, you will see a log singularity starting at minus 1. And then if you calculate the next guys, you will see that this is basically an expansion of a function multiplying this logarithmic cut. Similarly, you could do the same for these P guys. And this is an expansion of a function multiplying log 1 minus T, this logarithmic cut starting at 1. And similarly, this guy suppressed by 2 to the n, it will give a logarithmic cut starting at 2. And these guys will be the expansion of this function which multiplies that cut. So the notion of the alien derivative basically associates for this function to its singularity, so like delta plus minus 1 or 2, it's exactly expresses this function which multiplies the logarithmic cut by its expansion, which you can get from the asymptotics. So what I introduced here is that this alien derivative is a very good notion. It parameterizes the logarithmic cut. And you can read off this function, the expansion of this function, the large n asymptotics of the original coefficients. Okay, so let's see how we could calculate these alien derivatives in our case. So I analyzed this f alpha. I normalized to start with 1, this expansion. And then I use this, I will use this Richardson transform I already explained to suppress the 1 over n corrections in the Borel plane. So, and I would like to read off the asymptotics. And then usually I got numbers like I put here. I know these numbers much more digits because I told you I know them for like 7,000 digits. And even after some research on transforms, still a lot of digits. And I already told you that Ferenc Niedermayer, when he calculated the mass gap, even for, I don't know, 8 or 6 digits, he could figure out that this number should be 8 over E. And actually, I didn't know for such an ugly number what it is, but my collaborator János, who also worked similar models, he suggested that it should be like here in this case minus E over 8 pi. And indeed, if you calculate this asymptotics by Richardson transforms, and then you multiply with your 8 pi divided by E, then you will see that this is minus 1 for 150 digits. So it's like digging out some non-trivial information from these nasty coefficients. And then what you do, once you know the asymptotics, you just subtract this asymptotics, and then you multiply by n, and then you repeat the similar analysis. So I'm saying you can get this coefficient, like e to the 8 pi, from the asymptotics, and then you see the next coefficient is 0 for 147 digits, and then the next one, usually you calculate just the ratio of this coefficient divided by p minus. And for example, here in this P2 guy, you will get a number, and then you take the ratio. It doesn't look like anything. I think this is exactly the number I put here on the top. But there is a very nice web page, and then I put it here, this easy face web page. So you just take this big number, say truncate to 50 digits. You go to the web page and you plug in and you ask, so what combination of the zeta functions 1 and zeta 3 is this function? And then this web page gives you the answer. So it's very nice. You have some number, you don't know what it is, and then you can, using this interface, you dig out some magic expression. So it's basically like in this case -1/2 -3/4 times zeta 3. So what you already know your number with very high precision, and then you just ask this question for 50 digits, but then you can subtract it and you see this is valid even for 140 digits. So this is a kind of I don't know, like Bitcoin mining. It's like mining. You are mining coefficients out of the numerics, what you have. So we mined these coefficients, which is basically the alien derivative of this function at -1. This is the function multiplying the logarithmic cut starting at 1. And we could get the first 9 coefficients in terms of zeta functions very basically exactly, although observing at very high precision. But we also could calculate like other 40, 50 coefficients numerically. So this is how we calculated from the asymptotics. And then when you calculate, this was the odd part of this series, the asymptotics. And you can focus on the even part, and you will see that you have only the first guy is non-zero. All other guys, it's easy to fit. You can see for decreasing but many digits that they are 0. So this confirms that this singularity, what we could see in the body approximant, is really a pole. Okay, you can subtract this pole, re-expand your function, and you can also fit this other coefficient, which is the alien derivative of your original function at 2, which means the function multiplying the logarithmic cut starting at 2. So once we know this function, once we know these singularities, we could visit this integral, this inverse Borel transform, when you integrate a bit, say, above the real line. And since you already know this singularity is much better by these alien derivatives, you know the residue of the pole exactly, and you know these first few coefficients, then you see that the imaginary part of this function in terms of this already fitted coefficients, which we believe these are exact, of course. And then you can just compare the numerical values to the previously fitted values what we obtained by comparing the conformal mapping and the numerical solution of the TBA, and then you see they agree for the digits, we believe it was correct. So we understood very well now this imaginary singularity, imaginary ambiguity, sorry, the imaginary deviation. But what about the real ambiguity? We would like to understand these D coefficients. So in order to understand this D coefficient, so we did this integral after the conformal mapping, and we integrated, say, a bit above. But what happens that we already have seen the contribution of the pole, say, and the next cut, and we identified this function which multiplies, say, the first cut. But this function by itself is also asymptotic. So this function also has a cut. So when we integrate, and then we see how this function jumps integrating above and below, we have to take into account the cut of the cut, because it will also introduce a jump of this function. And there is a nice theory behind which takes care of all of this. And this goes under the name the Stokes automorphism. And once you calculate all the alien derivatives, you can express how the function, this integral, jumps once you cross these singularities. So the claim is that if you calculate this integral a bit below and above, and you make the difference, then the difference can be expressed in terms of these alien derivatives. It takes, the first few is just the jump of the logarithmic cuts when you have just one delta. But if you have more deltas, this is exactly the contribution of the cut of the cut. And then the reason why I introduced these alien derivatives, because once you know the alien derivatives, you can define this Stokes automorphism, what is written here, which is basically the exponentiated form. And it will tell you how this integral will jump if you jump from above to below. So this is called the Stokes automorphism. But in order to get the physical result, we would like to have something which is unambiguous when we jump. So the way we can do it is done by the median resummation. This is one suggestion how we could get a real and ambiguity-free result, although we don't know if it will be the physical result. But it's defined like you already know how your function changes if you jump. So let's integrate above and additionally take half of this contribution from the jump. So you take the square root of the Stokes automorphism, and this is how you can define a physical quantity, which is hoped to be the same what we could get from TBA. So if you calculate it, then you will see that we will have this single alien derivatives, just the contributions of the cuts. But at some point we also have some, and these are imaginary, but at some point we also have some real part, which is related to the second alien derivative of this function. This is the alien derivative of the alien derivative, the asymptotics of the asymptotics. This is the cut of the cut. So we in order to have and to see this real deviation, we need to calculate this D2F. So this delta 2F is basically the jump of delta 2, which is in the asymptotics of delta 2. So we have to calculate the asymptotics of delta 2. And then actually we didn't have enough coefficient to calculate this asymptotics because we had only 1,400. But I will tell you what the result was, and it's a kind of spoiler. So if you use this median resummation, then you will see that there is a correction at e to the minus 8 over alpha, and then we could calculate these two coefficients, actually first three coefficients by fitting the asymptotics of the asymptotics, basically to be 1. I mean 32 over e to the 4, and then the ratio was 5 over 8. And then if you compare these quantities we already calculated from the numerics, then you will say they completely agree. So that's what we did. But I can explain how we did it. But maybe it's a good point to stop and see what's the time. So how much time do I have?
I think like -1 minute.
Yeah, that's I guessed. So
Okay.
I will be quick here, and then if you have question, then I'm happy to go into the details. So because we have more coefficients in this rho and epsilon, so we analyzed the asymptotics and calculated these alien derivatives for rho and epsilon. And here we observed something quite incredible. We don't know the origin, but the alien derivative of this rho and epsilon can be expressed in terms of this epsilon and rho. So we don't know why, we don't know the origin, but it is really beautiful. We calculated the alien derivative. There was no pole here, there was a pole here, and this function multiplying the cuts, they were completely new functions. And then we analyzed these functions, and then here we could calculate in this variable the asymptotics of the asymptotics, this r of b and epsilon of b, and that we could translate. So in this median resummation, using this more precisely measured delta 2R, delta 2E, we could calculate these quantities in terms of these exact values. And then once we calculated, first it matched the previous fitting in the precision we expected these numbers were correct. But additionally, we could suggest the physical value of the solution of the TBA, and in terms of this non-perturbative and perturbative resummed contributions, and that we could compare directly to the TBA solution, and they agreed. And this is written how it agreed. So what is the structure of the final result expected? I mean, this is like, should be like TBA. This is the physical quantity we calculated. This should be a double expansion. So it's like a transseries. One expansion is the perturbative coefficient. But every perturbative expansion is multiplied with some exponential factor. From the first few terms, it seems like this. So the physical quantity is the original perturbative expansion, plus we have some exponentially factor times another perturbative expansion, and then we have higher and higher order exponential terms, and they are related to each other such that if you calculate the usual perturbative coefficients, then the large N asymptotics will tell these other pieces, other sectors, and then if you calculate the asymptotics of these other sectors, it will tell you what is the expansion, perturbative expansion of the next terms. And this is exactly what we did, first few orders, and we checked against this numerical solution of the TBA equation. So I will stop here, and thank you for your attention.
Okay, let's thank Zoltan for this nice talk. Let me pause the